Okay, we are going to continue graphing these linear inequalities in two variables, but now we're going to talk about them as a system. So this is 5.7, systems of linear inequalities. This is going to be just like doing systems of linear equations, except now we are going to take everything that we did before in 5.6 and we're going to graph 2, 3, sometimes even 4 of these systems in the same coordinate plane, and we are going to get a solution set that's true for all of them. So here we go. First example, y is less than 2x and y is greater than or equal to x plus 1. So here's a system of linear inequalities. It's the exact same one we graphed in 5.6 notes. Letter A is going to have 3, 5, and I will say letter B, we're going to use the ordered pair 220, or negative 2, 0. Our question is, are the ordered pairs solutions? Remember, in order to be a solution to a system, it needs to be true for both. And that's going to be the case with these inequalities here. So in letter A, I have an x, I have a y. I'm going to do exactly what I did before, except now I just need to test it in both of them. It needs to be true in both. So here, my y is 5. Is 5 greater than 2x, and x is 3. Actually, I switched my sign. Should not have done that. 5 is less than 6. Ask yourself, is 5 less than 6? Yes, it is. That checks. It's not a solution for the system yet, it's a solution for this part of the system. In order to be a solution for the system, it has to be true for both. I will plug that in. Y then is 5 is greater than or equal to x, which is 3, plus 1. 5 greater than or equal to 4. That is true. So yes, 3, 5 is a solution or part of the solution set for this system of linear inequalities. I will do the same on B. You have an x, you have a y. 0 less than or equal to 2 times negative 2. 0 less than negative 4. Is 0 less than negative 4? No, it's not. It's greater. That's no. Does not check. I can certainly check the next one, but soon as I get a no, doesn't matter if it's true for the second one. If one of them's no, it's not a solution to the system, because remember, it has to give me a true statement for both. 0 would equal, or 0 is greater than or equal to x, which is negative 2 plus 1. 0 greater than or equal to negative 1. That certainly checks. But because it is not true for both, this is no. The ordered pair negative 2, 0 is not part of the solution of that system. Here's how we get into the graphing though, and this is the Again, the nuts and bolts, what holds everything together, and the important part of it. So graphing these systems. And we're going to graph them the exact same way we did in 5-6 with our boundary lines. They could be solid, they could be dashed. With our solution set, our shaded regions, but now we're going to have regions that overlap. And we're looking for what's the solution set for both of them. What ordered pairs are true for both? Y is less than x plus 2, and I'll say y is greater than or equal to 2x minus 1. First thing you want to do is get your boundary lines. Do these look like y equals mx plus b? They certainly do. That's super nice. On my first one here, I have a slope of 1, a y-intercept or a b of 2. On my second one, I have a slope of 2 and a b or a y-intercept of -1. This is what I need to graph. This is what I'm going to make in my coordinate plane. So I'm going to make a quick little xy coordinate plane. Something that looks like this. Not terribly fancy, but nice and clean and crisp. Y-intercept of 2, slope of 1. I will plot 2 on the y-axis. Leave my pencil. Slope of +1, that is going to rise. I am going up 1, over 1, and I'm going in both directions to continue this out, because, and remember, I'm looking for the solution for it. I've got to go to my inequality to look at, is this a solid or a dashed boundary line? And this one is dashed because there is not an equal to it. So I'm going to put it on here. And when I go through here, I am going to make this a dashed line in both directions. Just like we did in 5-6. Now, I got to look at my shading. And if I do what I did in 5.6, I can either look at this and say, hey, I want y's that are less than this boundary line. You want y's that are below it. Y's that are less than this boundary line are lines that are below it. My shading is going to be below this line. If you want to test it, test a point that's not on the line. What's an easy one to test? 0, 0. I'm going to say test 0, 0. I've already determined that because I'm going to want y's that are less than this boundary, my shading is going to be below here. But I'm certainly going to test 0, 0 because some of us like to test it, and I still do go back and forth for sure. X is 0, y is 0 into this first inequality. 0 is less than 2. Is that true or false? Well, that's true, which means 0, 0 should be part of my solution, which means I want to shade to this side of the line. And notice, I'm not shading in yet because with a system, we are going to shade what they have in common. But I'm going to put some little arrows there to know that, hey, I am definitely concerned with this part of this graph. Shading would be to this part. But I've got a system. I've got to get 2 of them in there. We're going to shade what they have in common. What's true for both of them? Graph this line. It's going to be solid, my boundary line is, because there's an equal to. It has a y-intercept of -1, which is right there, and a slope of 2. Up 2 over 1. Up 2 over 1. Up 2 over 1. Up 2 over 1. I can go down 2 to the left 1 and I've got that line right there. There it is. It's got to be solid because it's got that equal in it. And I'm going to pencil that in. Now I've got to determine which side of the line I got to shade on. And again, if I want y's that are greater than this boundary line, that's going to be y's above it. That's where y is getting bigger. You're going to want to shade to the left of this line. Or you could test 0, 0 in the second equation. I'll say that again. Test 0, 0. Why do I choose 0, 0? Because it's easy. And because I've already determined that I want y's greater, I should get a true statement with here, including the origin with the shading of this, meaning my shading should be going this way. Well, let's test it. 0 would be greater than or equal to 2 times x, which is 0, which would just give me -1. Is 0 greater than or equal to -1? It's certainly greater than, which means I would include that point 0, 0. I want to shade this way. Why do I draw these arrows? Because I only shade what they have in common. My solution is the area where they both are pointing those arrows to. It's what they have in common. It's the shaded region that's both of them, meaning any ordered pair that I pick in this shaded region is going to give me a true statement with these inequalities. Now, if I choose a point out here, it's going to be true for this one. For my first one there, the y is less than x plus 2, but it's not going to be true for this one. The only points that work for both of them are what lies in that double shaded region. And that's how we do those systems. Break it down, do them step by step, and then get what they have in common. Let's look at one that's amped up a little bit. And I'm going to go with a new piece of graph paper, and I'm going to say this example here. Let's do 2x plus y is less than -1. Two x plus y is greater than 3. And our directions are going to be the same. We are going to graph and solve. We're going to solve this. Graph it. Get what they got in common. In order to graph, and get it to look like y equals mx plus b. I'm going to move this 2x over, so it's going to leave me with y is less than a -2x minus 1. I will do the same for this one. This 2x has got to come over here. Is greater than -2x plus 3. Identify slope. (-2/1), a y-intercept of -1, slope of (-2/1), and a b of 3. Hopefully you're noticing right now if I have the same slope in two different y-intercepts, you're going to have some parallel lines here. But it really depends on which way your inequalities go, to whether if there's going to be no solution or I am going to get a solution, or what they're going to have in common. This is what I'm going to graph. I'm going to do that right now. Quick little XY coordinate plane here. Here's my X, here's my Y. First one, b of -1, y-intercept of -1, slope of -2. Your line is going to fall down 2 to the right 1. And I can certainly continue that down. and I will go up 2 to the left 1 to continue it in this direction. There's my line. Dashed, because there's no equal. Both of these will actually be dashed. So I'm going to put that in. And I'm going to make a nice dashed line connecting those points there. I need my shading. I can certainly test 0, 0, or if I have this rearranged, I'm looking for y's that are less than this boundary line, and y's that are less are below this line. That's what would be included in it. If you don't like that, test 0, 0. There's the origin. It doesn't lie on the line. If I get a true statement, I would include it. I've already decided that I should get a false statement, which means I'm going to shade away from this line, away from the origin. If I take this first original equation, look at that. That's 0 and 0. Is 0 less than -1? No, it is not. I would not want to include the origin in there. I took 0 for x, 0 for y. 0 plus 0 is 0. Is 0 less than -1? No, it's not. I would want to shade this way, not including that point, away from the origin on the other side of that boundary. I need to graph my other equation. 1, 2, 3 is my y-intercept. -2 is my slope, down 2 to the right 1. 1, 2 to the right 1. And as I can see, I have this parallel line right there. And it certainly looks parallel. It is going to be a dashed line as well, so I'm going to pencil that dashed line in. There's my boundary. It's dashed because there's no including the equals. And now I want y's that are greater than this boundary line. Well, if I look at it, y's are getting bigger above it. I think I'm going to shade to this side. I'm going to test 0, 0 just to be sure. 0 plus 0. And again, test 0, 0. 0 plus 0. Is 0 greater than 3? 0 is not greater than 3. I would not want to include this. That means I shade to this side of the line, and that's what my intuition told me. Do they have anything in common? Is there any overlapping of the shading? Are there any arrows that are pointing to each other? No, there are not. This one, I can certainly graph this system, but we may get them like this where they don't have anything in common. This is no solution. And just because the lines are parallel does not mean that I'm going to get no solution, because if I would have flipped this inequality sign on this one right here and shaded this way, then it's going to be shading including everything this way as well. So I just got to look out. If I don't have arrows that are pointing towards each other, could potentially get no solution there. The last thing we are going to do is we are going to write a system given a graph. So we are going to write a system of linear inequalities. Write a system of linear inequalities, and I got to make a little graph here. This is like the two problems off of 5.6 at the end where we're writing for one of them. Now we're going to write it for the system. Here's one of the lines. I'm going to say I have a vertical line. That's right there. Let me label that as X and Y so it becomes clear. There's one line. And then I am going to put a point, let's see, I'll go right there. I'll put a point right there. And I'm going to pencil that line in. This is just creating it. But I will make that as a dashed line. And then I will tell you that the shaded regions, what they have in common is right here. And we want to write the system of linear inequalities. So I've got this right here. I'm going to look at this vertical line. Hopefully you are recognizing that a vertical line is x equals, but it's an inequality. If this was just a line and I wasn't dealing with inequality, this would be the line x equals 3. So I have my x, and I know it's 3. What sort of x's am I concerned with? Well, what sort of x's are to the left of this line? X's that are getting smaller. We want x's that are less than or equal to -3, or not -3, to +3. Why is it equal to? Because that's a solid line. What's represented right here is x's that are less than or equal to 3. This line, I've got a y-intercept, and I can certainly get a rise over a run for slope. This line right here would be y, and if I just think of it as y equals mx plus b, to get from here to here, a rise of 2, a run of 3, you would have 2/3 x, and my y-intercept is -1. I've got to consider my shading. What's shaded are y's that are above that, where there are greater than. It is not equal to, so I would have that. This is what they have in common. There are my two linear inequalities represented by that graph when we started. We are going to certainly work through a lot more systems than we are just graphing individual ones. Once we know how to graph individual ones, the bulk of our time, the next 2 practice days, are going to be spent doing these, graphing these systems and writing these systems.